I present to you two pictures. One is a picture of a real child, a Google search picture, and another is a computer-generated one. Now I'll take a pause here for you to think which one is of a computer-generated image and which one is the real one. Now I've asked this question before and a lot of people have chosen A and some other people have chosen B. Now wait to the end of the presentation for you to find out which one. My name is Mekdi Yilma. I'm a data scientist, and for the remaining part of the presentation, we'll be going through the process and how it's like to generate computer-generated art. And in this presentation, we'll have a high-level overview of the project. We'll have an introduction to Generative Adversarial Network, commonly referred to as GAN, the workflow process that I used, some of the learning, what type of model I used, how I evaluated it, some of the real-world application, and we'll end with next steps. High level, we will use a Generative Adversarial Network, GAN, and its amazing ability to create unique digital images or data that has never existed before to generate abstract art collection. And GAN could be a little bit of a complex topic, but for this, I will peel the layers, go back to the foundation, and be able to paint you a mental picture of how the algorithm works and what its structure looks like. For GAN, we have usually two neural network models, one pitted against the other one. One is the generator, which we can think of in our case as the artist that tries to learn to create the images that look real. And we have another one called a discriminator, which in our case we can think of as the art expert that learns to distinguish between the real images versus the fake or generated images. And as presented here by the GIF, you can be able to see the interaction of the two models as represented by the artist and the art expert and how they learn from one another in order to create an image that looks real. The other type of GAN is Cyclic Generative Adversarial Network, also called Cycle GAN. And it essentially is an image-to-image translation that takes the characteristics of one image, that's the source image, and be able to translate it to the characteristics of the second image. And as you can see here, we have two generators that are used and two discriminators. So as relating back to our example, generator G, or one of the artists, tries to convert domain A to domain B, and the second artist tries to convert domain B into domain A. And we have two discriminators on each side, or two art experts that are distinguishing whether that's a real image or not. And in our specific case, I have used one domain as water to create an abstract inspired work from it. Now, the workflow I have instituted is to scrape license-free images using Selenium. And then majority of my work is spent on AWS using the machine learning service they provide, SageMaker, as well as S3 Bucket for data storage. And I have also pre-processed the data for compatibility and for some enhanced performance on the model. As I mentioned earlier, GAN, it is an unsupervised process, but it has a supervised aspect within it, which is the discriminator labeling a real image or a fake image. And it uses that to answer an overall of unsupervised question. And this is what the model structure looks like. It uses convolutional neural network. And here I have two important aspects of the convolutional neural network. One is downsampling data, which is essentially a layer that converts, for instance, here what we have is a 4x4 pixel and converts it back to a 2x2 using a kernel of a 3x3. And as you can see, a movement of, or a stride of 1. And upsample is simply a reverse of that, which is a transposed version of convolutional neural network. And another important aspect is how we process each of these layers. And for our case, we've used instance normalization. Some of the learnings I want to call out prior to us evaluating the model is CycleGAN. It can be very expensive in terms of training as well as memory, and it requires high GPU. And for that, I was able to use Amazon's one of their fastest instance to be able to compute my data. It takes longer training time. When I used it locally, one epoch could not run on my local computer. However, using Amazon service, one epoch took about 40 minutes. Another important call out is I was able to store a lot of checkpoints throughout the process in case anything happens, to be able to revert back and start from halfway through or whenever it stopped, and to finally be able to restore the model as well. And finally, as I mentioned before, using S3 bucket for better performance. Before the training the model, we have the input image, as you can see on the left side, and what the right side shows is what it spits out on the first run, and that is just essentially noise. As it trains multiple times, I've run my model for 50 epochs. This is what the prediction looks like. And finally, as I mentioned before, with unlearning, unsupervised learning, there is no specific error metrics to evaluate the model, but there's one clever way, which is looking at the real image and comparing it against the cycle image. So essentially, the real image is supposed to be the exact replica of the cycle. Here, using our visual instance, we can see that they're both pretty similar. So that means our model is working great. And one of the real world application could be trading these abstract arts in the NFT market space. And some of the artwork that's generated here is a sample from the CycleGAN I ran. What are the next steps? Well, we can use a training API that Amazon provides for faster performance, and that will allow us A, to run more epochs, and B, to hyper-tune our model to find the best fitting ones. This is my information. And prior to ending the presentation, I will go back to the first question I asked you and give you the answer. So child B was the one that was generated by GAN. Thank you.